Hi everyone, and welcome to the third weekly webinar for the Udacity Deep Reinforcement Learning Nano degree. Hi everyone, and welcome to the third weekly webinar for the Udacity. Sorry about that, I had a feedback loop with the sound. My name is Willie Proshak, and in this webinar we'll be covering the Monte Carlo and Temporal-Difference and extend from the Markov decision process that I went through last week and explain how they sort of integrate together, the differences, and just go into both of those algorithms in more detail. I'll also be doing some talking about some other topics leading up to that to help explain how they work, and hopefully that will give you a better understanding of why we use a particular algorithm and what their benefits and disadvantages are. I hope that this week's has been really good for all of you in study and that you've learned a lot. You know, you're almost through the introduction stage and start getting on to looking at actual DQ networks and value-based algorithms. So first, I'm just going to go over what we'll cover. So basically I'm going to start off with prediction and control, on policy and off policy, episodic continuous tasks, model-free methods, Monte Carlo approach, exploration, exploitation trade-off, epsilon greedy policy. Then I'm going to go into the temporal difference approach, then SARSA, QLN, and then sort of compare them all and have a bit of a summary. So hopefully this will give you enough understanding to go ahead and implement either a Monte Carlo or Temporal-Different approach, or at least give you a high understanding. So first, what I'm going to do in this webinar is just cover some of the prereqs before we go into the algorithms themselves. So I'm going to talk about prediction and control. So RL tasks are pretty much separated into two different tasks of either prediction and control. Prediction is the type of task that predicts expected total reward from any given state, assuming the function policy AS is given. It basically does a policy evaluation. And control, this is the type of task that finds the policy AS that maximises the expected total reward from any given state. Policy iteration is the combination of both to find the optimal policy. So that's, you know, and both the Monte Carlo and the Temporal-Difference algorithms both have these two particular tasks, which we'll go into more detail later. On policy and off policy is the next bit that I'm going to talk about. So there are two types of policy learning methods. On policy learning, it learns on the job, which means it evaluates and improves the policy that it's used to make a decision. It's directly learning the policy, which gives you decisions about which action to take in some state. Off policy learning is a bit different. It evaluates one policy, the target policy, while following another policy, behavior policy, just like we learn. So basically observing others and then doing the same thing. So the target policy may be deterministic, greedy, while the behavior policy is stochastic. So hopefully that makes a bit of sense. Now the other topic which I'm going to go over is episodic continuous tasks. Now I talked about them last webinar, but I think it's good to just recap them just because of the way the Monte Carlo and the TD algorithms work. So an episodic task lasts for an episode, which basically means that it has a finite amount of time. So one of the examples would be playing chess, playing a particular stage, and it sort of finishes. A continuous task never ends, and that something like that would be trading, for example, the cryptocurrency markets, or learning machine learning, or anything that's just continuous. It doesn't actually have a start and end point directly. This course, for example, would be episodic, or the actual each part, but your learning of reinforcement learning and deep RL is probably going to be for a continuous task for the rest of your life. Now, one of the things we'll talk about is model-free methods. So with dynamic programming, which you would have looked at this week as an option, what a model, so the main thing about dynamic programming is that you get the transition properties and rewards. But what happens if you don't get that? What do we do then? So then we use a model-free method. So it basically focuses on the value function directly from interaction with the environment. So the learning algorithms learn value functions directly from the environment themselves. And that's what I'll be talking about next. So the Monte Carlo approach. So the Monte Carlo is probably one of the first main algorithms that you'll learn within reinforcement learning. It learns the value function directly from episodes of experience. So it gathers episodes and learns from that. With a Monte Carlo approach, we only get the reward at the end of an episode. So for example, an episode is there. So for example, state 1, action 1, reward 1, and then the next state 2, action 2, reward 2, and so on and so on and so on until the terminal state. One of the other things that you need to know about Monte Carlo, it takes the mean of the episodes. So e.g. if it was 1, 2, 3, 4, it would be 10 divided by 4 equals 2.5. So hopefully that's something quite important with Monte Carlo, and hopefully this sort of clarifies it from what the course content went through. And there's two main methods within Monte Carlo approach, which is the first visit Monte Carlo and the every visit Monte Carlo. So the first visit, we average the returns only on the first time the state is visited in an episode, while every visit, we average returns every time S is visited in an episode. So they are the sort of two main methods within Monte Carlo, and I'll go ahead and go into more detail on that. So going back to before where I talked about prediction and control. So the first part of Monte Carlo, the prediction, I'll go over the pseudocode. So the first visit Monte Carlo policy evaluation. So pretty much it initializes all the values, and then the first thing it does in a loop, it generates an episode using the policy. For each state of S appearing in the episode, it gets a return for the first occurrence and adds that to returns. It then gets the value BS, which is an average of those returns. So pretty much it goes ahead, generates all these episodes using the policy, and then gathers them all up, and when it's finished, it averages them all up and works out the value for the state. Next, so what I've got here is the Monte Carlo prediction code. So the following snippet there, so generate episode function, is pretty much what it's doing. It is collecting and returning those state, action, reward tuples. So as you can see, we first initialize an episode list, and we get the current state. So that would be using just simple gem. We then get the action from the get action policy from the current state, and that's that there. So you get back from the state score, the dealer score, and the usable ace. And basically what it's saying is it returns 0 if the score is larger or equal to 20, else 1. What it then does, it next step, it gets the performs the action and gets the next state reward and whether it's done. We then add that, the current state action reward to the episode, and if done we break, and otherwise current state equals next. So that's the basics. So it's generating an episode, gathering all those details, adding them to a list, and then basically returning that. So this is the whole sort of loop for the blackjack using Monte Carlo. So same thing, initializes the return, the state count, and V, and then basically creates an episode. So it gets sample episodes, and then goes through and gets the SAR, so the state action reward, and then goes from there down and basically gets to the point where it's taking the mean of the episodes for calculating the V values. So hopefully that makes a bit more sense. What I would say is go through that in your own time and just go through in a bit more detail to understand it. Hopefully it's a pretty straightforward algorithm. And if you have any questions, of course, then ask you in the Q&A session. Basically, after it's finished, what you get from that is a default dict, which basically returns the state, those three details, which, if I go back, are that score, dealer score, and usable ace, which is just there. And then it returns the value for the state. So we get for every state. Now, what this is only representing is just a finite amount. It's not every single one of them. Keep them all on the page, but this gives you the value for that particular state that it sees. Now, before I go into Monte Carlo control, I'm going to talk about exploration and exploitation trade-off, because it's quite important. So in model-free RL, we need to interact with the environment to find out the best strategies. So we need to explore the entire state space while figuring out the best actions. The exploration is about finding information about the environment. So we want to explore as many actions and states that we possibly can, because the more information that we have, the better we'll be able to exploit that environment. While exploiting is basically from the known information is trying to maximize that reward. So this is really important in RL, and that's why we use particular things like greedy action selection, or epsilon greedy, and why epsilon greedy is important. So as you can see, say there was two doors, and on the left door you open it and you got 0. And then you went to the right door and got +1. If you were using greedy action, you would just keep on using the right door over and over again, as you see in the slide. So next thing gets 2, then 2 again. But have we actually chosen the right door to maximize reward? Possibly, or possibly not. As you can see, the fact that we're getting different levels each time we look at the right door means that we're potentially getting the same on the left. So it could even be as simple as we have a 90% chance of getting +10 and only a 10% chance of getting 0. If that's the case, the best option right now would be to choose left, but we don't know that because we haven't actually gone through and explored enough details. And so that's why we use epsilon greedy policy. So the basics of an epsilon, it's between 0 and 1. The best known action based on our experience is selected with 1 minus the epsilon. Probability, and the rest of the time, the epsilon probability, any action is selected randomly. Initially, the epsilon is on 1 so that we can explore more, but as we do many iterations, we slowly decrease the epsilon to 0, which is exploitation, choosing the best known action. The other thing that we can do is set the epsilon, for example, to be 0.1 or 0.9. So it'll either most of the time will do random, or it will, but what we're trying to do is choose the right actions so it can kind of go further in the task, but we're also wanting it to just explore a bit. So it's a bit like if you're playing a video game, or you're have a particular action. So if you say it's a video game and you do the same actions every single time, you won't ever get any better. But what most people do is they try something different, or it could be if you're playing sport, they might try kicking the ball different or shooting a different way, and it may not work most of the time, but it may be really good, and so you've added that to your knowledge as a better way of doing things. And that's the most important thing with is that exploitation, exploring. So if you don't explore enough, you're never going to find all the best possibilities. So epsilon greedy is a great way of doing that. Now that we've sort of gone through a bit of that, I'm going to go on the Monte Carlo control. So it's an on-poly first use of Monte Carlo control. So basically, at the beginning, we initialize QSA, returns, policy, and basically we do a loop. We generate an episode using policy. For each pair SA appearing in the episode, we get the returns of SA. We add that to D to returns SA, returns SA, and then we get the average once again. And then for each S in the episode, we basically, the argmax is the optimal action that it knows, and basically we pretty much go from there. So I'll go, look, probably the easiest way is to look at it in code. So once again, I've got the generate episode and the epsilon there. So what we've got is, once again, we construct, or we initialize the episode list, and we get the first date. We then, the prop score, so basically get epsilon greedy action policy Q current. So that's over on this side, which is this function. So it initializes a numpy with 1s, and then times epsilon divided by NA. The best action is argmax of the Q observation, and the best action is determined, but with 1.0 minus the epsilon. So if the epsilon is 0.1 and the epsilon, the epsilon is 0.1, so basically you've got 1, which would be always picking the best action, and then if you minus the epsilon, it's of 0.1, it would only pick the best action 90% of the time. So 10% of the time, it will basically do a random choice, and that gives you a bit of, it starts looking at, different ideas. And one of the things you can do is actually reduce that over counts. So you go from randomly looking at everything to, by the end, you're only doing the best actions, and maybe only 10% of the time doing a random observation. So it may get down to the point where the epsilon is 0.9 and the best action is 1, minus 0.9, which would then mean that it only does random 10% of the time. So you understand how that, it's quite important, and epsilon greedy is great for that. And the rest of it is pretty straightforward. So goes through very similar to the last. So I'll just go on to a bit more of the code. So this is the whole loop. So the Monte Carlo control epsilon greedy function that adds them all together. So basically initialize a default dict for Q, and then we do a loop. Once again, create episodes, generate episode based on Q. Once again, you get this state action in an episode. which is the SAR in the episode. For each ISA pair, we basically get both back the state action from SA pair. Once again, we sum that up, and we're basically taking the means of the episode for calculating the Q values, and then it returns Q. So what it's returning is this again. But this time, what we have is the values for each function, sorry, for each action for that state. So here's the state, and then we've got the best action to do. So that would be either hit again or hold. And as you can see, these all have values. Now you've done any deep learning or anything like that in the past. These, you get these out, say, from TensorFlow. Usually argmax them, of course, to get the right action that you want, and pretty much go from there. So hopefully that sort of explains a little bit more about Monte Carlo control. And now I'm going to go on to temporal difference approach. So temporal difference is a combination of Monte Carlo and dynamic programming. So just like Monte Carlo, TD method learns directly from episodes of experience and is model free. But just like dynamic programming, TD methods bootstrap. So it's meaning you not wait until the end of the episode to update the expended future reward, estimation V. You'll only wait until the next time step to update the value estimate. Now this is quite important in some tasks, especially continuous tasks that don't have an episode themselves. So this is a great way to implement for continuous tasks. While Monte Carlo just couldn't work in that method, or you'd have to frame the problem from continuous to episodic. So the TD prediction, so once again, I'll go over prediction and control. So a little bit different. We basically input is the policy to be evaluated. We initialize B, and basically after that we repeat for each episode. We initialize S, repeat for each step of episodes. The action given by the policy for S, and take action A, observe, reward, and next state. And then we run the below function until basically S is terminal. The code for it, so there's two bits to it, is the get action policy and the TD prediction. So the get action policy takes in the state, and basically from that it gets the score, deal score, and the usable ACE again, so the same as Monte Carlo, and then returns a NumPy array similar to before. So if we look at the prediction, create, once again, initialize d.dict for V, and we start off, get the current state, while true, we get the problem scores, so using get action function above with the current state, and then the current action is a NumPy random choice of NP range NA and the prob P, which equals the prob underscore score. Next, from that point, we do the action in the next step of the environment, and we get a normal next state reward done. We then, the TD target equals reward plus gamma times V next state. TD error is TD target minus V current state, and then V current state equals V current state and alpha times the TD error. But don't worry if you don't get that straight away. Probably the best way would be to just go over this a bit like reinforcement learning over and over again until you get it. And if you I've been doing the code for the TD or Monte Carlo. A good way is to put out print statements for each return, so you can actually see what's going on and have a look at how things are built. Once again, it returns similar stuff, so these the state details and then value is returned, and so it's very different. It's very similar to the Monte Carlo, but as you can see, slightly different. So just like the Monte Carlo, we use a policy iteration for TD control. The first step is to learn an action value function rather than a state value function. There are two main algorithms in TD control, which I'm going to go through, which is SARSA and Q-learning. So what I'll do first is go over SARSA. Now, SARSA, basically the agent starts, say, in S1, performs action 1 and gets reward 1 and goes to S2. Now the agent chooses another action, action 2 from state 2, then updates the value of A1 performed in S1, then gives the above equation, sorry, as you can see from the above equation, or actually side equation now. So S, the current state, A, current action, and R, the current reward. The next state, and then the next action. The TD target is R plus gamma and Q of the next state and action, and the TD error is R plus gamma Q next state and action minus the current Q value for the state action. If the next state is terminal, then Q next state equals 0, so it has a value of 0. So basically what we're doing is we're getting the reward plus a discounted for the Q value of the next state action and minusing the current Q value state action pair. So SARSA is a state action reward state action. So what that basically means here in the pseudocode, it's a non-policy TD control algorithm. Once again, initializes all the main values and then repeat for each of them. So to initialize S, use A from S, use the policy derived from Q, and repeat for each step. So we take an action A, observe the reward and next state. We choose in the next action from the next state using the policy derived from Q, the Q value. So QSA, and then you basically QSA plus alpha R plus gamma Q next state action minus current Q value SA, and then goes to from the state to the next state and action to the next until the S is terminal. So I'm hoping that makes a bit of sense. But once again, go over the pseudocode and go through the actual code itself, and hopefully that will make a bit more sense. So once again, I've got some code for it. So once again, this is similar to before, but slightly different. We've got the Q and the observation. So not just the observation. So once again, initialize A, we get the best action, which is the argmax from the Q observations. The best action is once again got the epsilon, so it has the probability of choosing the best action. The SARSA function here basically puts that all together. Once again, initializes, performs a loop which gets the current state, the probability scores, and the current action. And then while true, it gets the next state, reward done. So it's the probability scores for the next state, the next action, and then goes down to getting the TD target, TD error, and Q for the current state and current action. which basically equals the Q current state current action plus alpha and the TD error, which is the TD target minus the Q current state and current action. So the TD target was the reward plus gamma times the Q value for the next state and next action. So once it's done, if done, current state equals next state, current, so, and then basically returns the Q. Those Q values look like this. So that basically gives you those Q values. Hopefully makes a bit of sense. So next I'm going to go on to Q learning, which is the other main algorithm. So Q learning is one of the most important breakthroughs in reinforcement learning and was the development of an off-policy TD control algorithm. Q learning estimates a state action value function for the target policy that is deterministically selects the action of highest value. So the agent starts, for example, in S1, forms A1, gets reward 1 and goes to state 2. Same as SARSA. The other agent looks for the maximum possible reward for the action in state 2, then updates the value of A1 performed in S1. Once again, same as SARSA, and then gives the above to the equation there. So basically, the current state, current action, current reward to the next state. So next is the next state and the next action. So basically, the TD target is the reward plus gamma max of the next action given for the Q value of the next state action. The TD error is reward plus gamma argmax basically of the next action, given the Q value for the next state action minus the current Q value for the state action. Once again, if the next state is terminal, it gets a reward of 0. So next, I'm just going to go over pseudocode. So once again, initialize everything and then set in a loop. So chooses A from S using action from state using the policy derived from the Q value, takes an action A and then observes back the reward and next state. And as you can see, so you've basically got QSA, QSA plus alpha, reward plus gamma, the max of the Q for the next state given the action minus the Q value for the current state action pair. And then the state goes on to the next state until S is terminal. Once again, here's code. So the epsilon greedy action is pretty much the same, and the Q learning. So what you can see is once again, initialize gets the best action, uses the epsilon. Best action is based on epsilon. So the while loop gets the probability scores from the get epsilon greedy action policy, which is given the Q value in current state. The current action is basically an NP random choice for given NP range NA and the P or probability scores. From there, it performs the action and gets returned the next state reward action. And then it gets the best action by doing a argmax of the Q next state. TD target equals reward plus gamma times Q value of the next state and best action. And then the TD error equals the TD target minus Q value of the current state and current action. And the Q current state current action equals the Q value for the current state current action plus alpha plus the TD error. If done, it breaks and current state goes next and returns the Q values, which look like this. So what I'll do next is going to go on talk to about the main differences between SARSA and Q-learning. So as you can see, that's for SARSA, and this is for the Q-learning. So basically, SARSA is on-policy learning method, means it uses the same policy to choose the next action. While Q-learning is off-policy learning, meaning it uses the target policy greedy, choose the best action, the next action, while following the behaviour policy epsilon greedy. So, the other thing which I'm going to go into more detail on is the differences between the Monte Carlo and TD methods, so you can understand the main differences between the two. So Monte Carlo only works for episodic tasks because it needs to gather all of them at the end of the episode. It can only learn from complete sequences. It has to wait until the end of the episode to get the real world. So this could be a massive problem, say if you were trying to teach a car to drive, because you'd have to crash or you'd have to have it into a simulator. Or if you were doing a continuous task, it would almost be impossible. Once again, you'd have to frame that task as an episodic task. The TD method works for both episodic and continuous tasks, so it's more versatile. It can learn from incomplete sequences, and it will only wait until the next time step to update the values. So this is great, for example, if you're trying to learn something on the fly, like once again, trading currencies on the fly, or doing anything that doesn't have that end, and you want to kind of have a bit better idea as you're going. TD is probably a bit more versatile than Monte Carlo, but Monte Carlo still works incredibly good if you can, look at all the state action pairs and do a good exploration. It will work incredibly well. Now, hopefully that sort of covers most of what we've gone through for this webinar. So the main things that I wanted to point out was we use model-free algorithms when transition probability, the dynamics of the system, is not given in the MDP. We also, Monte Carlo takes the mean of the episodes to calculate the V and Q values for both prediction and control tasks. TD combines the features of both dynamic programming and Monte Carlo by learning through interacting with the environment with bootstrapping. We use epsilon greedy policy to avoid the exploration problem in environments, and SARSA updates the Q value by choosing the current action and next action using the same policy, making it an on-policy method. Q-learning updates the Q values by acting greedily on the environment while following another policy, making it an off-policy method. So hopefully that makes a bit of sense. The main difference between SARSA and Q-learning. I think Q-learning is quite a very, very powerful and basically it's what the deep Q-learner is based upon. They've added, for example, a policy is a neural network, and they have other things like experience replay and so on. But it's basically an extension of Q-learning. So that's all I have for today. So I'm hoping that sort of gives you a good idea of the main two algorithms in reinforcement learning. Which is Monte Carlo methods and temporal-difference methods, and then going into more detail in the temporal-difference methods of SARSA and Q-learning. So before I finish up, a few references that I used. So introduction to Richard Sutton, David Silver's video lectures, and a Medium post. Now, If any of you have any questions, please post them in the chat and I'll try to go through them now. Otherwise, if you've got some questions down the track, post them in the Slack channel or direct message me if you have any questions. Or if you're not sure, maybe go over the parts of the video again. It will be available online as a recorded, which I'll put into the Slack channel soon so that you guys can do any catch-ups if you missed it. So once again, thank you very much for this webinar. And I'll just wait a couple minutes to see if there's any questions and try to respond to them. All right, so no one's got any questions. That's all good. Look, like I said, if you have any questions down the track, once you've sort of gone over it, or maybe watch sections of the webinar again, let me know. And hopefully you enjoyed this and it was easy to understand. It was going into a bit more complexity than previous webinars, but I'm hoping that it explains, especially Monte Carlo and Temporal-Difference methods in a bit more detail and how to apply them. Thank you very much, and I'll see you guys next week.